Uh, Hello everyone. So in today's video, we'll be going to learn about one of the important topic, which is finite state machine. So before we jump to the finite state machine, I think everybody knows about the combinational circuit and the sequential circuit. So as we know in the digital, uh, there is a combinational circuit and a sequential circuit. So in combinational circuit, the output depends only on the applied input value and not on the past history, which means the output will depend only on the applied input at that point of the time. Suppose, for example, if you are taking a full ladder, so whatever it will be having inputs as well as the output, which will be sum and carry. So whatever input we are applying, the output sum and carry would be generated based on the applied input and not on the depending on the previous history. So basically whatever input which has been applied in the past. So coming to the sequential circuits. Now in contrast to the combination sequential circuits, outputs generated depends of course on the applied input value, but also on the past history, which is represented by an internal state. So in the simple example for this, if we consider suppose a binary counter. So just to say, we are considering a 4-bit binary counter that counts from 0 to 15 and then again back to 0. So now suppose if the value of the count is 4 and if you are applying a clock to output and you'll be expecting output to be 5, and that will depend not only on the clock, which is your input, as well, but it will also depend on the previous count value, which was 4. So this previous value can be regarded as the state of that machine. So we see that the next output which are getting, that is dependent on some previous information, which is the state as well as the applied input. So now moving forward, so also we can say that the internal state also change with time. So in real life scenario, for any practical hardware implementation, the number of states should be finite. It can't be infinite for some obvious reason, because ultimately it will be representing the a flip-flop. As we see that count, as we have seen in this counter example, the 4-bit counter which will be storing a 4-bit of information. So here we will be requiring 4 flip-flops. And if I say that if there is infinite number of state, then it is impractical to build such a machine as it will require infinite number of flip-flops. And because of that only reason, this practical sequential circuits are also referred as a finite state machine. So there, as we can see, there is a concept of a state, number of state, which is finite, and there is a formal definition of a machine. So most importantly, from this, we can say that most practical circuits which we see around us are sequential in nature and only few are combinationals. Now moving to the next slide. Here we have taking a finite state machine, which in short which we say as FSM, can be specified or represented in the form of a state table or in the form of a state transition diagram. Here we can see that a state transition diagram is there. So in this example, a circuit is there to detect a three or more number of ones in a serial bit stream. Means that here I am assuming that there is a one input where sequence of bits are coming one by one, like 1 0 1 1 0 1 1 1 continuously. Here, if I want to find out 3 consecutive ones or more consecutive ones are there or not in this sequence, and every 3 consecutive ones, the one will be detected as an output, single bit output, which will go to 1. Otherwise output will remain as a 0. So this is the state transition diagram, and there is how it is depicted in this example. That is the circuit to detect three or more ones. This the state table description. As you can see, there is a state table description, and this is the equivalent state diagram. So now let us explain the first state diagram, which will be easier to understand, and then we can jump to the state table. So here we can see that there are four circles A, B, C, and D, which indicates the state of a machine. From there, we can see how many states are there, which will be required for a particular description, which depends on the problem specification. So different problem specification will have a different number of states. For this case, as we are trying to detect three consecutive ones, so it will require at least four states, and this four state, it has been signified by A, which is an initial state, B means which have seen a single one so far, C means we have seen two consecutive ones, and D, which means we have seen three consecutive ones so far. So we will be requiring four states because we have detected three consecutive ones. And here the notation used are like 0/0, as you can see, 1/0, 1/1, which are refers as the first before the slash, the zero is as an input, and after the slash, whatever the value is, whether it is 0 or 1, it is an output. So this circuit has a single input and a single output. Now suppose I'm in a initial stage. When we reset the when we reset, if the start is like from it is starting from A. Now if we are getting an input value 0, it will remain at the same state, at state A only. So I'm waiting for the next one actually. Whenever if I'm getting 1, I go to the next state, and so the notation will be like, as you can see, 1/0. So as still I haven't got consecutive three ones, so the output will remain as a 0. As we have been moved to next state, that is B. So as will B remember the its value, the information. So I have seen a single one, means B remember that it has the information 1. So if in the B, if we are getting another one, I go to the next state, which is C, and similarly for the C, here we see that if we see another get another one, then it will be moving to the next state, which is D. So after getting three consecutive ones will be detected, and while the output will become 1. So here we can see that in D, if one we get more, after that also we are getting 1, then the output will be remain at 1 only. So, and if we are getting, like suppose we are in another state, and if we are not getting the input as a 1, so it will be going back to this previous, like in the if we are in the state B, and if we are getting 0, we'll be moving back to state A. Similarly, if we are in the state C, and if we are getting next input value as a 0, we'll be moving to state A. Now this same information can be depicted in the state table, and this state table indicates the input, and here we can see my input are reset and input value, and have a single output. So additionally, I have a notion of a state, which can we call as a present state or PS, and next state as a NS. So now moving forward, so the idea is that if my reset is high, as we can see in the first row, first column, so irrespective of the present state that and the applied input, my the next state, the next state will be A only. As we can see that NS is A, and the output will be 0. So here, if the reset is 0, and the operate, then only the operation will be start. So if the present state in A and the input is 0, then I go to the next state, which is A, and with the output will be 0, which is indicated by the arc, as we can see that uh, in the first state. Similarly, if my present state is A and the input is 1, so my the next state is B with the output 0, because as we has not detected consecutive 3 inputs. So for every edge in this state transition diagram, we have one row in a table. So we can see weekend, which is equivalent representation. So now the state diagram is easily understandable as the state table looks. So it is very convenient to go for the state transition diagram, because a state table, it's a little bit looks a little bit jumbled and the complex to interpret. Now there will be, as we know that there are two types of FSM, which are Mealy machine and another is a Moore machine. Let's see what are these. So before we go to the Mealy and the Moore finite state machine, let's discuss a bit about a deterministic FSM or deterministic finite state machine, which means whenever we apply an input, whenever I know the state, so the next state and the my output will be absolute deterministic. So basically all the practical circuits which we see are deterministic, but for modeling, or you can say for theoretically consideration, another kind of FSM is also there, which we define as a non-deterministic. But for the practical reasons, for the practical design point of view, we will be considering only a deterministic finite state machine. So this deterministic finite state machine can be mathematically represented. As you can see, so many symbols has been used, like sigma, gamma, capital S, S naught, delta, and omega, where sigma denotes the set of input combination. So for example, if you are considering two inputs, so there will be maximum 4 input combination like 0, 0, 0, 1, 1, 0, 1, 1. And similarly, for 3 input, it can have a maximum 8 input combination from 0, 0, 0 to 1, 1, 1. Similarly, gamma indicates the set of all the outputs. And, and similarly, it can have all the possible combination depending on the number of outputs, whether it is 2 or 3. Now here S denotes a set of state, and a small s naught, which is a member of S, denotes the initial state from where we have started. And delta is defined as a state transition function, and omega is an output function. Now, if you see, now delta is defined as a gamma, which is the definition, and capital S and sigma, which is the Cartesian product of a given state and a given input, and it will determine the next step. So this actually tells us about what will be the our next step. So now that is the present state and the present input definition and next step. Now for the output function for the Mealy and the Moore machine, we have a difference actually. As far as the Mealy machine, the output will depend on the state as well as the input. So for this, this equation will be like omega equal to S cross sigma giving delta. And for the Moore machine, it will be, as it will depend only on the state, omega equal to S, omega is the definition, S giving to gamma. So now moving to the pictorial representation of this Mealy machine and the Moore machine, which can be seen in this slide. So if we see it closely, for the both Mealy and the Moore machine, two functions, one is the next logic and another is an output logic. The next logic is a function which takes the primary input and it takes the present state, which is stored in a flip-flop or a memory, and it generates the next state. Here the next state, as you can see, it is a combinational logic, and the output logic is again similar actually. So, and for the Mealy machine, It takes a primary input and present state, and it generates the primary output. So we can see for the Mealy machine, there's the output is dependent upon the primary input as well as the state. But in the case of Moore machine, we can see that output is dependent only on the present state and not on the input. So now moving forward, we'll be just taking an example. So in every day-to-day life, we have seen this traffic light signal controller. So if you are taking, there are three lights are there. Here, red, green, and yellow. And the from circuit, as we can see, there is a three output line, and that is green, yellow, and red. And the clock signal is coming, which is an input. So this three red, green, and yellow color has to glow cyclically, which is at the fixed interval of time. Suppose here we have taken for the 10 seconds. So we can clearly see in this FSM we are having a three state, as it has to remember the color of the lamp actually, and which has to be glow. There red, yellow, and green is a state. So means as it has to remember the state, so means if the last time it was suppose green, so it has to be yellow next time, or if it was red, then the next time it has to be green, which can be captured by the state transition diagram. So red, green, green, yellow, and so on. So this is an example of a basic Moore machine, as the output depends only on the state, and it is not on dependent on the input, and there is no input here in this example. So some of the application, if we can see for this finite state machine in the real time, is like design and implementation of different type of sequential circuits like counter, timing controller, and other. It is used in the digital control system to control the and regulate the behavior of a couple of complex automation systems and others. So overall, this is all about the finite state machine, which is basically in practical life or in real life scenario, it is mostly used. So it's all about finite state machine. Thank you.